Hey guys, tonight on Slumber Expeditions, we descend to the very bottom of the Mediterranean Sea, not to explore its sunken cities or its marine life, but to uncover a time when the sea itself was gone. We will journey back to a period when the azure waters that cradle civilizations vanished, leaving behind a silent, scorching desert 2 miles deep, a basin of salt under a blistering sun. Our exploration will uncover the monumental geological forces that sealed the Mediterranean off from the world's oceans, transforming it into the most immense salt pan the planet has ever seen. We will walk the vast, dry plains of this lost world, witness its dramatic and violent resurrection in a cataclysm of water, and trace the evidence, locked in the seafloor, that proves this incredible event is not a myth, but a foundational chapter in Earth's history. This is a story of a sea that died and was reborn. So before you settle in, if you're finding comfort in these deep time cataclysms, please consider liking this video and subscribing to the channel, but only if you genuinely like what we do here. We would also love to hear from you in the comments below. Tell us where you are listening from and what time it is there. It's always fascinating to connect with a global community of curious minds who share this fascination with our planet's greatest enigmas. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's speculative journey together. Let the gentle rhythm of waves that were once absent guide you into a story of unimaginable change. You are standing on the deck of the American research vessel, the Glomar Challenger, on a sweltering day in 1970. The ship is holding position over the abyssal plain of the Western Mediterranean, off the coast of Spain. Beneath you, kilometers of blue water hide the seafloor. The crew is engaged in a daring feat of engineering, drilling into the deep ocean bottom from a floating platform. A pipe string miles long connects the ship to a drill bit chewing through sediment. When the core barrel is hauled up and its contents carefully split open on deck, the scientists, led by Dr. William Ryan and Dr. Kenneth Sue, expect to find the familiar layers of ooze and clay, the gentle rain of marine life accumulated over millions of years. But instead, something astonishing is revealed. Beneath the normal sediments lies a layer of hardened salt, not just a dusting, but a massive formation, hundreds of meters thick. It is a mineralogical anomaly of staggering proportions. In the depths of the ocean, they have found the bedrock of a desert. This is the moment of discovery, the first tangible, irrefutable evidence that the serene Mediterranean holds a secret of epic dryness at its heart. This single core sample, pulled from the dark depths, was the key that unlocked one of the most profound geological mysteries of the 20th century. The initial discovery by the Glomar Challenger was not an isolated fluke. It was the catalyst for a systematic, basin-wide investigation. Over the following years and decades, numerous oceanographic expeditions, employing ever more sophisticated technology, returned to the Mediterranean to test this radical hypothesis. Each new drilling site told the same impossible story. From the Balearic Basin to the Ionian Sea, from the foot of the Nile cone to the deep trenches off the coast of Greece, the drill bits consistently encountered that same stark layer of salt. It was not a local phenomenon, not a pocket of minerals trapped in a submarine canyon. It was a continuous stratum, a blanket of crystallized ocean that lay beneath the entire seafloor like a hidden foundation. The sheer geographical spread of the evidence was the first compelling argument that this was not a minor event, but a catastrophe that had gripped the entire basin. The true scale of this hidden landscape began to emerge not from physical cores alone, but from the ghostly images of seismic reflection profiling. This technology allowed geologists to see through the deep sea sediments without drilling a single hole, Powerful air guns sent sound waves pulsing through the water column and into the seabed. These waves would travel down, reflecting off the different layers of rock and sediment, and their returning echoes were captured by long arrays of hydrophones towed behind the research vessels. When these signals were processed, they produced detailed cross-sectional images of the Earth's crust, like sonograms of the planet's subsurface. And in every single profile, a brilliant, continuous reflector appeared, a sharp, clean line that geologists named the M reflector, the M standing for Messinian, the geological age of this event. This M reflector was the top of the salt layer, and it echoed from beneath millions of square kilometers of seafloor, providing a map of a lost world. It showed the salt layer pinching out against the continental slopes, filling the abyssal plains, and even draping over submerged seamounts. It was the cartography of an absence, the sonic signature of a sea that was not there. The composition of the material beneath the M reflector was just as revealing as its extent. When the drill cores were analyzed in laboratories, they told a complex chemical story. This was not a simple layer of table salt or halite. It was a structured sequence of evaporite minerals, each one forming at a specific stage of seawater concentration. The cores showed layers of gypsum, a soft sulfate mineral that forms early in the evaporation process, often in beautiful, crystalline forms like the desert roses found in arid regions today. Beneath the gypsum, they found vast, thick beds of halite, the mineral that precipitates when the water has lost most of its volume and the salinity becomes extreme. In some of the deepest basins, they even found potassium and magnesium salts, like sylvite and carnallite, which are the final, bitter dregs of a dying ocean, the last minerals to crystallize out when the water is almost gone. This precise layering, this chemical stratigraphy, was a clear and unambiguous record. It was the story of an entire ocean basin slowly boiling away, not once, but repeatedly, with each cycle of flooding and desiccation leaving its own distinct chemical signature in the rock record. The logical and inescapable conclusion from this evidence was that the Mediterranean had been isolated from the world ocean. A body of water this large cannot simply evaporate if it has a constant, open connection to replenish it. The geological search thus turned to the gates of the Mediterranean, the Strait of Gibraltar. Today, this narrow channel is the sea's lifeline, but the tectonic history of the region, driven by the slow, relentless convergence of the African and Eurasian plates, revealed a different past. This continental collision was not a single, shattering impact, but a slow, grinding process that periodically squeezed and uplifted the land bridges of the western and eastern ends of the sea. The Betic and Rif mountain chains in southern Spain and northern Morocco, along with possible land bridges in the Middle East, acted like tectonic valves. At times, these valves were closed. The research indicated that around 5.96 million years ago, these portals sealed shut. The Mediterranean was transformed from a thriving sea into the world's largest terminal lake, a captive body of water with no outlet, utterly dependent on the delicate balance between the inflow from rivers and the relentless demand of the atmosphere. With its oceanic life support severed, the Mediterranean was living on borrowed time. The mathematics of its situation were brutally simple and utterly unforgiving. The surface area of the sea is enormous, acting as a vast evaporating pan under the hot subtropical sun. The input from rivers like the Nile, the Rhone, and the Po, while significant, was a mere trickle compared to the volume of water lost to evaporation every year. The hydrological budget was catastrophically negative. The sea level did not just slowly fall, it began a precipitous plunge, dropping at a rate that is almost unimaginable in our stable modern world. It is estimated that the level fell by over a centimeter per year, a descent that would have been visibly dramatic over a human lifetime. As the water retreated, it exposed a bizarre and ever-expanding new continent, a landscape of recently submerged marine clays, silts, and sands, now baking dry under a cloudless sky, a world that was being born from the receding waters, a world of utter desolation. As the Mediterranean's level continued its relentless fall, the single, unified sea began to fracture. The underwater topography, once hidden beneath a uniform blanket of blue, now dictated the final stages of its demise. The deep abyssal plains, some plunging more than 4 kilometers below the former sea level, became the last refuges for the dying body of water. The Mediterranean shattered into a series of massive, hypersaline lakes, isolated from each other by the rising sills of submerged ridges and seamounts. A great lake formed in the Ionian basin, another in the Tyrrhenian, and others in the Aegean and Levantine basins. These were not bodies of water as we know them. Their surfaces were often stagnant, choked with thick, soupy brine. The water, devoid of oxygen and saturated with salt to the point of being syrupy, took on a sinister character. It could be a milky, opaque white from suspended gypsum crystals, or a deep, bloody red from blooms of salt-loving, pigmented bacteria, the only life that could endure these toxic conditions. The vibrant marine ecosystem of the open sea was now a distant memory, replaced by a sterile, chemical soup in which nothing else could survive. The process of evaporation is a powerful geological force, and in the confines of these shrinking lakes, it began its meticulous work of mineral deposition. As the water volume decreased, the concentration of dissolved salts increased exponentially. The first minerals to surrender to the changing chemistry were the carbonates. Fine particles of calcite and aragonite, the building blocks of limestone, began to precipitate out, forming a chalky layer on the lake floors. Then, as the salinity doubled and tripled compared to normal seawater, the sulfates began to crystallize. Vast fields of gypsum formed, their crystals growing in the shallow, warm waters at the edges of the lakes. In some places, these crystals grew into enormous, translucent selenite sheets, meters long, lying in chaotic, glittering piles like the shattered glass of a celestial window. These gypsum deposits now form significant geological formations around the Mediterranean rim, silent witnesses to the first phase of the Great Drying. But the most dramatic deposition was yet to come. As the lakes shrank further, approaching their final stages, the concentration of sodium and chloride ions became so overwhelming that the water could no longer hold them in solution. The great halite precipitation began. This was not a gentle process. It was a massive, basin-wide event where halite crystals nucleated and grew, sinking through the water column in a continuous, slow-motion snowstorm of salt. This salt snow accumulated on the lake floors, building up in thick, dense layers. In the deepest parts of the basins, where the final, most concentrated brines pooled, the halite layers are hundreds of meters thick. They are often banded, with subtle variations in color and crystal size, each band representing a seasonal cycle or a minor refreshment from a river flood, a rhythmic layering of time in a world where time itself seemed to have stopped. These are the deposits that now form the mighty M reflector, the definitive proof of an ocean turned to stone. The climate within this deep, dry basin would have been one of the most hostile and extreme environments ever to exist on Earth. The basin floor lay as much as 3 kilometers below the global sea level, creating a world of high atmospheric pressure. The surface of this new continent was a blindingly white salt pan, a perfect reflector of solar radiation during the day, yet it absorbed enough heat to create furnace-like conditions. Temperatures at the surface likely soared to 80 degrees Celsius or more during the day, hot enough to make the very air shimmer and distort vision, and to make any exposed rock too hot to touch. At night, with no cloud cover and little humidity to trap the heat, the temperature would have plummeted, perhaps to near freezing. The diurnal temperature swing would have been violent, a daily cycle of thermal shock that would have fractured rock and salt alike. This new landscape was also scoured by powerful, unpredictable winds. As air cooled and densified over the high continental plateaus of Europe and North Africa, it would have cascaded down into the deep basin, accelerating into ferocious katabatic winds. These winds, funneled by the topography of the dry seafloor, would have whipped across the flat salt plains, picking up fine, abrasive dust and salt crystals. Immense dust storms, far larger than anything seen in the Sahara today, would have been a common occurrence, blotting out the sun and scouring the landscape with a corrosive, salty blast. The sound of this world would have been a haunting one. The constant, moaning wind, the crack and pop of expanding and contracting salt crusts, and an overarching, profound silence where the sound of waves had once been. The rivers draining into this new, deep depression were confronted with a geological imperative. Their base level, the ultimate destination of their flow, had dropped by thousands of meters. In response, they unleashed a frenzy of erosion, down-cutting into their own beds with explosive energy. The Nile, no longer a placid river emptying into a wide delta, became a torrent carving a canyon so deep and vast it rivaled the Grand Canyon. This ancient Nile canyon is now buried under millions of years of sediment, but seismic surveys reveal its stunning profile, cutting deep into the African continental shelf. The same was true for the Rhone, which carved a monumental gorge now hidden beneath the Gulf of Lion and the Ebro in Spain. These Messinian canyons are the silent, submerged scars of this event, testament to the awesome power of rivers suddenly granted a 3-kilometer head start on their journey to the center of the earth. This entire hellish cycle was not a one-time event. The geological record within the salt layers shows a fascinating complexity. Between the thick beds of halite, there are layers of silt, clay, and even fossilized microbial mats. These sapropel layers indicate periods when the rate of evaporation slowed, or when freshwater inflow from rivers temporarily lowered the salinity, allowing a brief, tenuous resurgence of life in the form of algae and bacteria before the relentless sun and closed gates once again pushed the system back into hypersalinity and eventual desiccation. This suggests that the isolation of the Mediterranean was not perfectly static. There were likely brief, partial reconnections with the Atlantic, perhaps as tectonic adjustments or massive erosion events temporarily lowered the Gibraltar sill, allowing a pulse of oceanic water to spill in, creating a short-lived sea before the portal sealed again. For nearly 600,000 years, this was the brutal rhythm of the Mediterranean, a pulsating, cyclical agony of flood and drought, a planetary heartbeat of death and temporary reprieve, a story written in salt and stone. The profound silence of the empty Mediterranean, a silence that had persisted for hundreds of millennia, was finally broken not by a sound from within, but by a growing roar from the west. The tectonic vice that had held the Atlantic at bay was, at last, beginning to loosen its grip. The precise trigger for the end of the Messinian Salinity Crisis remains a subject of scientific inquiry, but the leading theory points to a combination of erosional and tectonic forces. It is possible that a precursor to the modern Guadalquivir River, flowing from what is now Spain, had been relentlessly cutting its way down towards the deep, dry abyss, slowly, but surely eroding the land bridge from its eastern side. Simultaneously, the complex tectonic stresses of the African-European collision may have caused a phase of subsidence, a slight dropping of the Gibraltar block. The result was a breach. What started as a trickle of Atlantic water finding a weak spot in the dam soon became a transformative event of biblical proportions. The difference in water level between the Atlantic Ocean and the floor of the Mediterranean basin was a staggering geographical disparity. With the Mediterranean largely dry, the Atlantic side of the Gibraltar sill stood over 1,500 meters higher than the basin floor. When the breach became significant enough, this difference in potential energy was unleashed in a cataclysm of flowing water. The resulting waterfall was the most magnificent and powerful the Earth has ever witnessed. It was not a single, narrow cascade like Niagara or Victoria Falls, but a wall of water that may have been several kilometers wide from the very beginning. A continuous, thundering curtain of ocean, over a kilometer high, plunged into the profound emptiness below. The sound would have been beyond deafening. It was a fundamental vibration of the planet itself, a deep, roaring hum that would have resonated through the rock for thousands of miles, a permanent seismic event audible across continents. This was not a deluge that filled the sea in a matter of days or weeks. The volume of the Mediterranean basin is immense, holding approximately 4 million cubic kilometers of water in its modern state. Even with a flow rate that modern estimates suggest was 1,000 times greater than the present-day Amazon River, the most powerful river on Earth, the refilling was a process that spanned a human lifetime, perhaps even a century or two. For generations, the Great Waterfall at Gibraltar was a permanent feature of the planet, a relentless, awe-inspiring, and terrifying spectacle. The waterfall would not have been static, it would have been a dynamic, migrating feature. The immense force of the falling water would have catastrophically eroded the soft sediments and rock of the sill, causing the waterfall to rapidly cut its way backward, westwards into the Atlantic, carving a deep and dramatic canyon in its wake. This ancient canyon, the U-shaped gorge of the Zanclean flood, is now completely submerged and buried under subsequent sediments, but its ghostly outline is still detectable in the seabed topography of the Strait of Gibraltar. The refilling process itself was a violent and turbulent rebirth. The initial torrent of cold Atlantic water would have crashed onto the scorching hot, salt-caked floor of the basin with explosive force. The contact would have generated vast, superheated clouds of steam, creating a permanent, impenetrable fog bank that would have shrouded the entire western Mediterranean for years. As the water level rose, it first filled the deepest western basins, like the Alboran and Balearic basins, creating a vast, new inland sea that was still isolated from the eastern Mediterranean by the submerged sills of the Sicily Channel and other underwater ridges. One by one, these sills were overtopped, creating their own, smaller but still spectacular, internal waterfalls. The entire refilling was a cascade of cascades, a series of monumental plumbing events as the sea reclaimed its lost domain basin by basin. The environmental and climatic consequences of this refilling were global in scale. This sudden introduction of a vast body of water into a region that had been a deep, hyper-arid desert for hundreds of thousands of years would have triggered a dramatic climate shift. The new sea surface would have begun to evaporate, but this time, the moisture was feeding into the atmosphere above a body of water, not a salt pan. This would have drastically increased humidity, leading to increased rainfall across southern Europe and North Africa, potentially ending a long period of regional aridity and transforming the landscapes of the continents that bordered the new sea. On a planetary scale, the rapid transfer of a significant volume of water from the global ocean reservoir into the newly filled Mediterranean basin would have caused a measurable, if temporary, drop in global sea level. This drawdown, estimated to be on the order of 10 meters or more, would have exposed land bridges around the world, potentially connecting islands to mainlands and opening new pathways for the migration of flora, fauna, and perhaps even early hominins. The legacy of the Zanclean flood, as this refilling event is known, is written into the very fabric of the modern Mediterranean. The thick layers of salt deposited during the desert phase were suddenly buried under a deep column of water and a new rain of normal marine sediments. But salt is a buoyant and plastic material. Under the pressure of the overlying layers, it has slowly but persistently flowed over millions of years, pushing upwards and piercing the younger sediments to form vast salt domes and diapirs. These structures are of immense economic importance as they create perfect geological traps for oil and natural gas, making the Mediterranean a significant hydrocarbon province. Biologically, the flood reset the clock. The native marine ecosystem had been utterly obliterated during the Salinity Crisis. When the sea refilled, it was recolonized by hardy species from the Atlantic that could survive the initial turbidity and changing salinity. This is why the modern Mediterranean fauna is notably less diverse than that of the Atlantic and is largely composed of Atlantic species, a living testament to a near-total extinction and a subsequent, slow, ongoing recovery. The calm, blue waters we see today are a mask, a tranquil surface over a history of unimaginable violence, a sea that remembers its own death and spectacular resurrection in the layers of salt beneath its floor. As we conclude this part of our journey into the vanished Mediterranean, we like to extend a special thank you for listening. If you're finding comfort in these geological explorations, please consider liking this video and subscribing to Slumber Expeditions. We would also love to hear from you in the comments below. Tell us where you're listening from and what time it is there. It's always fascinating to connect with our global community of curious minds. You can also share which part of a story has captivated you the most so far. It would be wonderful to start a conversation around it. Now, let the mystery of what we've uncovered so far settle in your mind as we prepare to continue our exploration. The cataclysmic roar of the Zanclean flood, as it poured for a century into the empty heart of the Mediterranean, did not bring a final, quiet peace to the basin. Instead, it initiated a new, slow-burning geological drama that continues to this very day, a silent, subterranean echo of the surface catastrophe that had come before. The floodwaters buried the vast, crystalline deserts of Messinian salt under a deep ocean and a steady, unending rain of new sediment, the fine, skeletal dust of countless trillions of plankton, the clays washed from the rivers of Europe and Africa, the sands of the Sahara carried on the wind. For a time, the evidence of the great drying was hidden, sealed away beneath a tranquil blue mask. But the salt itself had other plans. It was not a passive, inert layer. It was a geological instability waiting to happen, a restless ghost buried beneath the seafloor, and its long, slow movement would reshape the entire underworld of the Mediterranean. This ongoing process is known as salt tectonics or halokinesis, and it is driven by the unique physical properties of rock salt or halite. At the surface, salt is hard and brittle. But under the immense confining pressures and elevated temperatures found just a few kilometers down, it behaves less like a solid and more like a viscous fluid, a plastic material capable of flowing over millions of years. It is also significantly less dense than the surrounding sandstones, shales, and limestones. This combination of buoyancy and plasticity meant that the great, basin-wide salt layer, once buried, could not lie still. It began to stir, to slowly writhe and flow, its movements dictated by the uneven weight of the sediments piling on top of it. Where the sediment load was heaviest, the salt was squeezed laterally. It began to flow away from these zones of high pressure, seeking a path of least resistance, much like a blob of thick honey slowly spreading under its own weight, but on a scale of thousands of cubic kilometers and a time frame of millions of years. This slow-motion flight of the salt initiated a profound transformation of the Mediterranean's underworld. The first signs were the formation of what geologists call salt pillows, broad, gentle, regional uplifts where the salt was thickening, arching the overlying layers of sediment into vast, subterranean domes. These were not dramatic features on the seafloor, but deep-seated bulges, the first stirrings of the buried giant. As millions of years passed and the sediment load increased, this process accelerated. The salt pillars grew, their cores of mobile salt pushing upwards with increasing force. The overlying sediments, once flat-lying and orderly, were now being bent, stretched, and fractured. They were folded into complex anticlines and synclines, and sliced through by networks of faults. The entire geological architecture of the seabed was being remodeled from below by the relentless, upward pressure of the flowing salt. In the most dramatic instances, the salt did not just form gentle pillows or domes. It broke through. These are salt diapiers, where a narrow, piercing column or an extensive wall of mobile salt has forcefully intruded upwards through thousands of feet of overlying rock, sometimes reaching all the way to the modern seafloor. The process is one of the most powerful in structural geology. The salt, behaving plastically, can inject itself into fractures and force its way through strata that are far stronger and more brittle. It does not melt its way through. It shoulders the rock aside, a slow, irresistible force. From a hypothetical vantage point beneath the seabed, these diapiers would look like great, ghostly fingers of crystalline white salt reaching up towards the surface, or like frozen, subterranean rivers. On the seafloor itself, their presence is often marked by distinctive mounds and ridges that can rise hundreds of meters from the abyssal plain, or by pockmarks, mud volcanoes, and brine pools where fluids and gases migrate upwards along the fractures the salt created. The Mediterranean seafloor, for all its apparent placidity, is thus a dynamic terrain of hidden mountains and valleys sculpted not by water or wind, but by the slow, upward flow of the ancient, buried desert. This restless, subterranean activity has had profound and direct consequences for the modern world, most notably in the realm of energy. The very structures created by the flowing salt, the domes, the diapiers, the fault traps and anticlines, act as perfect natural containers for oil and natural gas. Over the millions of years following the Zanclean flood, organic-rich sediments, the remains of plankton and other marine life, were buried deep enough to be cooked by the Earth's heat. This process, known as thermal maturation, generated hydrocarbons from the fossilized organic matter. These newly formed oil and gas, being less dense than the surrounding water-saturated rocks, began to migrate upwards. They traveled through porous sandstone layers and along fractures, seeking a path to the surface. But their journey was often halted when they encountered the underside of a salt dome. The salt itself is impermeable, not even gas molecules can pass through its crystalline structure. The hydrocarbons became trapped, accumulating in vast reservoirs in the porous rocks adjacent to the salt, sealed by the salt's impermeable cap. This is why the Mediterranean, particularly areas like the Nile Delta Cone, the Adriatic Sea, and offshore Libya, are significant hydrocarbon provinces. The multi-billion-dollar search for oil and gas here is, at its heart, a geological detective story, a search for the architectural legacy of the Messinian Salinity Crisis. Energy companies use sophisticated seismic imaging to map the ghostly shapes of the salt structures. For to find the salt is to find the trap, and to find the trap is to find the potential for the energy that powers our modern civilization. Yet, this same geological bounty comes with a unique set of geohazards. The constant, slow movement and readjustment of salt structures can trigger small to moderate-sized earthquakes as the surrounding rock strains and fractures. More directly, the presence of salt diapirs can destabilize the seafloor. The flanks of these rising salt bodies are often steep and undercut, making them prone to massive slope failures and submarine landslides. These landslides can be catastrophic, potentially triggering tsunamis that could strike the densely populated coastlines of the Mediterranean. For engineers tasked with laying trans-Mediterranean pipelines or constructing massive offshore platforms, understanding the precise location, shape, and, crucially, the activity of these salt bodies is a matter of utmost importance. A seemingly stable and flat area of seafloor chosen for a pipeline route can become unstable if a salt diapir deep below decides to shift its position by just a few centimeters, potentially rupturing the pipeline and causing an environmental disaster. Furthermore, the seepage of hydrocarbons and saline brines along the faults that ring salt diapirs creates unique, isolated ecosystems on the seafloor, chemosynthetic oases where life thrives not on sunlight, but on chemical energy. These communities of tube worms, mussels, clams, and specialized bacteria are entirely dependent on the geological restlessness initiated by the salt, drawing a direct and elegant line from the apocalyptic dryness of the past to the isolated, thriving life of the present. The story of the Messinian salt is, therefore, a powerful lesson in the long-term memory and active agency of our planet. An event that concluded over 5 million years ago is not a closed chapter in a geological textbook. It is an active, ongoing process that continues to shape the geography, drive the economy, and foster the ecology of the region today. The salt layer is a geological engine, still running, its slow, inexorable movements a constant testament to the fact that the consequences of planetary scale events ripple through time for epochs, silently shaping the world beneath our feet and under our ships. The Mediterranean Sea, for all its surface calm and sun-drenched beauty, sits upon a foundation that is in constant, slow motion, a perpetual and dynamic monument to its own dramatic history of death and rebirth, a history written not in immutable stone, but in a mineral that refuses to be still. To comprehend the full impact of the Messinian Salinity Crisis, we must shift our gaze from the rocks and the salt to the life they once hosted, for this was not merely a geological event. It was one of the most severe and rapid biological catastrophes in the recent history of our planet. The Mediterranean Sea, before its isolation, was a thriving, diverse marine province, a part of the great Tethyan realm with a long and complex evolutionary history. It was a world of warm, clear waters, home to vast reefs built by corals and coralline algae, patrolled by sharks, rays, and countless species of bony fish. Its seafloor sediments teemed with burrowing worms, clams, and brittle stars, while its water column was rich with drifting plankton, the fundamental base of the entire marine food web. As the Mediterranean began its transformation from a thriving sea into a series of hypersaline lakes and finally into a salt-caked desert, this rich and intricate tapestry of life was systematically and utterly dismantled, thread by thread. The collapse was methodical and merciless, driven by the changing physics and chemistry of the water. The initial stages of isolation and rising salinity created a powerful and lethal environmental filter. The first to perish were the Stenohaline species, those exquisitely adapted to a narrow, stable range of salinity. The delicate, reef-building corals, which had flourished in the clear, warm waters for millions of years, could not tolerate the shifting ionic balance. Their symbiotic algae, the zooxanthellae that provided them with energy, were expelled, leading to bleaching and death. The magnificent coral reefs, vibrant underwater cities of color and life, became bleached, skeletal graveyards, their limestone frameworks soon to be buried by gypsum and salt. Most fish species, with their intricate osmoregulatory systems, the biological machinery that maintains their internal salt and water balance, were completely overwhelmed. As the surrounding water became a toxic, concentrated brine, their systems went into failure. They could neither absorb fresh water nor excrete the excess salt. Death for these creatures was not a sudden event, but a prolonged physiological collapse, a slow suffocation in a medium that was turning to poison. The devastation was not uniform across the basin, but it was comprehensive. As the water level dropped precipitously, vast areas of the continental shelf, the sun-drenched, nutrient-rich nurseries of the sea, the equivalent of the most fertile farmlands, were exposed to the air and utterly desiccated. Coastal ecosystems, including extensive seagrass meadows and perhaps mangrove-like forests that fringed the ancient shores, vanished entirely, their roots and rhizomes baked dry in the scorching sun. The loss of these critical habitats had a cascading effect, wiping out the countless juvenile fish, the invertebrates, the crustaceans, and the entire community of organisms that depended on them for food, shelter, and breeding grounds. Meanwhile, in the deep-water communities, adapted to a stable, cold, dark, and well-oxygenated environment, a different doom unfolded. As the water shallowed and the deep basins became isolated, stagnant lakes, the water warmed, and oxygen levels plummeted. The stable environment these creatures required was destroyed, replaced by a warm, toxic, anoxic brine. The final, absolute blow for almost all remaining life was the precipitation of salt itself. As the great halite layers began to form, they entombed the remains of the previous ecosystem, creating a sterile, chemical landscape where only the hardiest extremophile archaea and bacteria, thriving in the near-saturated brine, could persist. The Mediterranean had become a marine apocalypse, a biological vacuum on a scale rarely seen in the fossil record. This near-total extinction created a profound and empty void. When the Zanclean flood finally poured back through the Strait of Gibraltar, it did not bring the old Mediterranean fauna back to life. That world was gone forever, its unique evolutionary lineage is severed. Instead, the floodwaters offered a blank slate, a new, empty sea waiting to be colonized, a vast aquatic terra nullius. The first pioneers were the hardy, Euryhaline species from the Atlantic, the generalists, the robust swimmers, and the species with planktonic larval stages that could be carried by the powerful, inflowing currents. These were the biological equivalent of rugged explorers, capable of surviving the initial turbulence, the likely fluctuating salinity, and the barren, sediment-choked conditions of the newly filled basin. They were species like certain kinds of worms, hardy mollusks, and generalist fish that could tolerate a wide range of conditions. The recolonization was a slow, multi-stage process that likely took thousands of years to establish a stable ecosystem. The initial phase was a weedy ecosystem, dominated by a few opportunistic species that could rapidly exploit the new, largely barren environment, free from the competition and predation of a mature community. The recolonization of the deep sea was a particularly slow and fascinating process, a re-establishment of life in a world of perpetual darkness. The newly filled abyssal plains were a vast, muddy desert, devoid of the complex ecosystem of burrowers, filter feeders, and predators that characterize a mature deep-sea floor. The first arrivals were not the complex animals we might imagine, but bacteria and other microorganisms that could begin to process the organic matter slowly sinking from the surface waters. They were followed by the detritus-feeding pioneers, simple worms, sea cucumbers, and other invertebrates that could survive on this sparse food source, re-establishing a complex, multi-tiered food web with its intricate predator-prey relationships, specialized feeding strategies, and diverse niches took many millennia. This slow and incomplete recovery is a primary reason why the modern deep-water fauna of the Mediterranean is still relatively impoverished and lacks diversity compared to the Atlantic at similar depths. The deep sea here is a young ecosystem, still in its adolescence. The legacy of this profound evolutionary bottleneck is etched into the DNA of every creature that now calls the Mediterranean home. The modern marine biodiversity of the sea is notably lower than that of the adjacent Atlantic Ocean. It is not a center of unique, endemic marine life in the way an isolated island might be, but rather a subset, a filtered sample of the Atlantic fauna. This pattern is exactly what evolutionary biologists would predict from a near-total extinction followed by recolonization from a single source. The species that successfully made the journey across the Gibraltar threshold and managed to establish thriving populations were the founding ancestors of today's inhabitants. Some of these pioneer species, over the last 5 million years, have since evolved in isolation, becoming distinct species or subspecies found only in the Mediterranean, a process known as allopatric speciation. But their ancestral roots are unequivocally Atlantic. The crisis also had dramatic terrestrial consequences. The exposure of the seafloor created temporary land bridges, most notably between North Africa and Europe via what is now the Strait of Sicily, and between islands like Crete and the mainland. These emergent land connections allowed for the migration of terrestrial animals, including early elephants, hippos, deer, and rodents, which walked across the dry basin. Once the sea returned, these populations were stranded on islands, leading to the evolution of remarkable dwarf species, like the dwarf elephants of Cyprus and Sicily, whose fossils provide a poignant and parallel story of isolation and adaptation. The story of life in the Mediterranean is thus a dual narrative of profound loss and remarkable renewal. This sea we know today, with its familiar dolphins, tuna, sea bream, and octopuses, is a new ecosystem, a mere 5 million years old, a blink of an eye in geological time. It is a powerful testament to the remarkable resilience and dispersive ability of life to repopulate even the most utterly devastated of environments. Yet, its relative simplicity, its lack of deep evolutionary history and unique lineages compared to the Atlantic, serves as a permanent, biological memorial to the cataclysm it endured. Every fish that swims in its waters, every mollusk that clings to its rocks, is a descendant of a pioneer, a brave invader that crossed the threshold at Gibraltar into a new and empty world, a world born from salt and fire and a deluge of biblical scale. Unraveling the precise, moment-by-moment timeline of the Messinian Salinity Crisis has been a monumental task for geologists, a form of deep-time detective work that requires a forensic-level analysis of the rock record. The story is not written in a single, simple layer of salt, but in a complex, multi-volume archive of stacked sediments, each page, each paragraph, each subtle indentation holding specific clues to a different phase of the 600,000-year drama. The first and most crucial step in building this chronology was establishing a reliable, absolute timeline, a task achieved through the powerful, complementary techniques of biostratigraphy and magnetostratigraphy. Biostratigraphy relies on the fossilized remains of tiny, planktonic organisms like foraminifera. These microscopic creatures evolve rapidly, and distinct species exist only within specific, well-defined time windows in Earth's history. By identifying these index fossils in the marine sediments deposited just before the crisis, and then again immediately after it in the Zanclean layers, scientists could tightly bracket the event, pinning its beginning and end to a specific series of biozones in the late Miocene and early Pliocene. Magnetostratigraphy provided another, independent and globally synchronous clock. The Earth's magnetic field has reversed its polarity numerous times over geological history, and these reversals are faithfully recorded in the orientation of magnetic minerals as they settle out in sedimentary rocks. By extracting core samples and measuring the sequence of magnetic stripes in the Messinian and Zanclean sediments, and then matching this unique pattern to the global magnetic polarity timescale, the crisis was precisely anchored in time. It was this marriage of biological and physical dating that confirmed the event began with the isolation around 5.96 million years ago and ended abruptly with a Zanclean flood at 5.33 million years ago, a duration of approximately 630,000 years. Within this well-defined period, the sedimentary record reveals a surprising and intricate complexity. The crisis was not one long, unbroken period of extreme dryness. Instead, the thick salt layers are interbatted with layers of dark, organic-rich silt and clay, and with strange, crinkly laminations of fossilized microbial mats. These sapropel layers are the key to understanding the pulsating rhythm of the event. They represent periods of increased freshwater input into the isolated basins, likely driven by intensified monsoon-like rainfall patterns over North Africa, which temporarily lowered the salinity of the remaining lakes. This freshwater influx would have halted salt deposition and created a thin, fresher surface layer, allowing a brief, tenuous resurgence of algal and bacterial life. When these organisms died, their remains sank into the anoxic depths, preserving them as dark, organic-rich layers. The presence of these sapropels, occurring in regular cycles, indicates that the climate during the Messinian was not static, but pulsed with wet and dry phases, likely driven by the cyclical changes in the Earth's orbit and axial tilt, the same Milankovitch cycles that are known to govern the Pleistocene ice ages. The Messinian Salinity Crisis, therefore, was not a single event, but a series of dramatic climatic oscillations, each cycle pushing the basin to the brink of total desiccation before a temporary, orbital reprieve. The most detailed and visually stunning records of this chronology come not from the deep sea cores, but from the marginal basins and onshore exposures, where tectonic uplift has brought the entire sequence to the surface, laid bare in magnificent outcrops. In places like the Caltanissetta region of Sicily, the fantastic badlands of Sorbas in Spain, and the cliffs of Cyprus, one can walk through time and see the entire story exposed in the rock faces. This sequence typically begins at the base with the first cycle, gypsum, often forming beautiful, crystalline selenite layers deposited in the early stages of isolation when the sea was first breaking up into large, shallow lakes. Above this lies the main event, the thick, massive halite, the definitive signature of the most extreme desiccation phases. Within this halite, in exceptionally preserved sections, one can sometimes see individual varves, annual bands, much like tree rings. Each varve consists of a pair of a light, coarse-grained layer, representing rapid summer evaporation and crystal growth, and a dark, fine-grained layer, representing slower winter deposition and the inclusion of wind-blown dust. Counting these bands has allowed scientists to estimate the duration of the individual peak drying phases, confirming that they persisted for tens of thousands of years without significant freshwater input. In some sequences, the monotonous halite is suddenly interrupted by layers of fine-grained, deep-water limestone, indicating dramatic moments when the basin was suddenly and deeply flooded, either from a catastrophic river flood or a brief marine incursion, only for the gates to close again and the brutal evaporation cycle to restart. The event that finally and permanently ended the crisis, the Zanclean Flood, also left its own distinct and unmistakable signature in the rock record, a boundary so sharp it is one of the most recognizable timelines in the entire geological column. Immediately on top of the uppermost Messinian sediments, whether it is the final, paper-thin layer of salt, a last, desperate microbial mat, or the cracked and sun-baked surface of a mudflat, lies a sudden, erosional surface. This is the Zanclean unconformity. Above it, the sediments change dramatically and instantaneously. They are deep water, open marine blue clays and calcareous oozes, filled with the fossils of Atlantic planktonic foraminifera that had been absent for over 500,000 years. There is no gradual transition zone, no mixing of environments. The change is abrupt, absolute. This is the geological equivalent of a line being drawn in the sand of deep time. Everything below this line belongs to the alien world of the empty, salt-choked Mediterranean. Everything above it belongs to the familiar world of the refilled, open ocean. This boundary is so synchronous and distinctive that it is used by geologists worldwide to define the end of the Miocene epoch and the beginning of the Pliocene. Modern scientific drilling continues to add new, thrilling chapters to this story, refining our understanding of the flood's mechanics and power. Projects like the International Ocean Discovery Programme's Expedition 339 drilled into the Gulf of Cadiz, just outside the Strait of Gibraltar. There, they found immense, chaotic deposits of sediments and deep-sea gravels that were carried out of the Mediterranean by the powerful, density-driven currents generated by the inflowing Zanclean flood. These deposits, known as the Gilbert-type fan, provide direct, physical evidence of the flood's immense erosive power and its long duration. By combining the data from inside the basin, the salt and the sapropels, with the evidence from outside, the flood deposits, scientists are now able to create sophisticated, quantitative computer models of the entire event. They can simulate the flow rates, the erosion of the Gibraltar sill, the time it took to refill the basin, and the climatic impact. The story of the Messinian Salinity Crisis has thus been transformed. It is no longer a vague legend or a simple observation. It is a quantified, detailed, and dynamic historical account, a chronicle of a 630,000-year-long planetary drama, whose chapters are written in bands of salt and clay, whose paragraphs are marked by the fossils of vanished life, and whose final, breathtaking sentence was written by a waterfall that roared for 100 years, forever changing the face of a continent and the destiny of a sea. As we conclude this part of our journey into the vanished Mediterranean, we'd like to extend a special thank you for listening. If you're finding comfort in these geological explorations, please consider liking this video and subscribing to Slumber Expeditions. We would also love to hear from you in the comments below. Tell us where you're listening from and what time it is there. It's always fascinating to connect with our global community of curious minds. You can also share which part of the story has captivated you the most so far. It would be wonderful to start a conversation around it. Now, let the mystery of what we've uncovered so far settle in your mind as we prepare to continue our exploration. The epic of the Mediterranean's desiccation and rebirth is not a story locked away in geological textbooks. Its echoes resonate powerfully through the entire span of human history, subtly shaping the very stage upon which the drama of Western civilization would unfold. The colossal forces that emptied and refilled the basin did not simply create a geological curiosity. They sculpted the physical and perhaps even the mythological landscape that cradled our earliest cities, our greatest empires, and our most enduring stories. Consider the very ground beneath some of the world's most fertile regions. The immense, deep canyons carved by rivers like the Nile, the Rhone, and during the Mediterranean's low stand were not merely temporary features. When the sea returned, these monumental gorges, some rivaling the Grand Canyon in scale, acted as massive sediment traps. They were filled to the brim with layer upon layer of silt, sand, and clay carried down from the continents, creating vast, flat, and incredibly fertile alluvial plains. The Po Valley in Italy, one of Europe's most productive agricultural heartlands, and the expansive Nile Delta in Egypt, the historic breadbasket of empires, are direct beneficiaries of this process. Their rich soils are, in a very real sense, a gift from the Messinian Crisis, the legacy of sediments that choked these ancient, sunken riverbeds and then spread out as the sea level stabilized, creating the ideal conditions for the dawn of agriculture and the rise of complex, sedentary societies. The very configuration of the Mediterranean coastline, so integral to the development of maritime trade and culture, is a direct legacy of the Zanclean flood and the subsequent interplay between rising waters and a drowned landscape. As the basin refilled, the rising waters did not simply lap against a static shore. They inundated a complex, deeply incised terrain that had been shaped by millions of years of subaerial erosion during the dry period. The lower reaches of river valleys were drowned, creating the iconic, steep-walled, and deep inlets known as rias. These are spectacularly evident along the Dalmatian coast of Croatia, where a submerged mountain range has created a labyrinth of sheltered channels and harbors, and in the calanques of southern France, where narrow, steep-sided inlets cut into limestone cliffs. These natural harbors provided perfect, protected anchorages for the early seafaring cultures of the region. The Minoans, the Phoenicians, and later the Greeks did not simply find a coastline. They inherited a maritime landscape pre-engineered by geological catastrophe. The complex, island-studded geography of the Aegean Sea, a result of the submergence of a mountainous terrain, created a sea of steppes, a maritime highway where sailors were never far from sight of land. This geography fostered not just trade in goods, but the exchange of technologies, languages, and ideas, fundamentally influencing the development of democracy, philosophy, and naval warfare in classical antiquity. The sea that was a unifying force for human civilization was, in its very shape and structure, a product of its own catastrophic near-death and resurrection. This leads to one of the most tantalizing and speculative questions in geomythology. Could a distant, cultural memory of this event have persisted into human consciousness? While the last of the Great Drying ended over 5 million years before the first hominins walked the earth, the concept of a colossal, world-altering flood is one of the most universal and enduring myths across human cultures. From the Mesopotamian epic of Gilgamesh, where the god Ea warns Utnapishtim to build a boat to survive the deluge sent by the Council of Gods, to the biblical story of Noah, to deluge myths in Greek, Hindu, and indigenous American traditions, the theme is recurrent. Geologists and historians have long pondered whether localized post-glacial flooding events, such as the filling of the Black Sea around 5600 BCE, could be the source. But the Zanclean flood was an event of a different order of magnitude entirely, the most dramatic single hydrological event in the recent geological history of the entire region. It is a captivating, though ultimately unprovable, thought that the descriptions of a world drowned, of a deluge of unimaginable scale lasting for generations, could be a deeply buried, cultural memory of the refilling of the Mediterranean, passed down through an unimaginable chain of oral tradition, morphing and evolving over hundreds of thousands of years before finally being codified in the foundational texts of civilization. The sea that gave birth to so many of our foundational stories may, in its most dramatic moment, be the ultimate source of the greatest story ever told. In our modern, technological era, the legacy of the Messinian salt continues to directly impact the lives of the nearly 500 million people who live in the Mediterranean basin, dictating patterns of wealth, risk, and resource management. The ongoing process of salt tectonics, the slow flow of the buried salt layers, does more than just create hydrocarbon traps. It also generates significant natural hazards that require constant monitoring. The movement of salt can destabilize vast sections of the continental slope, creating oversteepened, unstable sediments prone to massive submarine landslides. These landslides, occurring in a confined basin, have the potential to displace enormous volumes of water and generate devastating tsunamis that could strike densely populated coastlines with little warning. Understanding the location, geometry, and, crucially, the current activity of these salt structures is therefore not an abstract academic exercise, but a critical component of national hazard assessment and coastal planning for countries from Spain and Italy to Greece, Turkey, and Israel. Furthermore, the same salt layers that are a source of wealth for the oil and gas industry can pose a direct threat to vital freshwater resources. In coastal aquifers, the drilling of water wells can accidentally penetrate or create pathways to these deep salt layers, leading to the upward migration of brine and the salinization of precious freshwater reserves. This is a particularly acute concern in a region that is already one of the most water-stressed in the world, where climate change and increasing demand are putting unprecedented pressure on limited resources. Today, the Mediterranean Sea is facing a new, anthropogenic crisis, one that eerily and unsettlingly echoes the processes of its deep past, but compressed into a terrifyingly short, human timescale. Climate change, driven by greenhouse gas emissions, is causing global sea levels to rise, threatening iconic coastal cities like Venice, Alexandria, and Barcelona. But perhaps more pertinently, the Mediterranean itself is becoming hotter and salter. Its nature as a concentration basin is being amplified by global warming, which increases surface evaporation, and by the damming and diversion of its major rivers, such as the Nile, which drastically reduces the inflow of freshwater that dilutes the sea. While it is not facing anything close to the total desiccation of the Messinian Salinity Crisis, the fundamental principle is hauntingly familiar: a severe and growing disruption in the delicate balance between evaporation and replenishment. The sea is once again becoming a more effective concentrator of salt, its deep waters becoming warmer, salter, and more stagnant, leading to expanding dead zones where oxygen levels are too low to support most marine life. This modern ecological crisis, compounded by pollution, overfishing, and the invasion of species from the Red Sea via the Suez Canal, is a stark reminder of the fragility of this ecosystem. It is an ecosystem that is still, in geological terms, a young and recovering patient from a near-fatal trauma, now being subjected to a new suite of stresses. The ghost of the Messinian past thus serves as a sobering, planet-scale warning of how dramatically and completely a marine system can be transformed when its fundamental hydrological and climatic balances are profoundly upset. The human relationship with the Mediterranean is therefore a continuous, often unconscious, dialogue with its deep history. We build our glittering cities on its reshaped shores. We extract the energy that powers our societies from the salt structures formed during its death throes. We draw life-giving freshwater from the sediments deposited during its violent refilling, and we navigate waters that were once a barren, sun-scorched desert. Our oldest myths may whisper the faintest echo of its traumatic rebirth, and our most advanced science allows us to read the intricate story written in the rocks and salts beneath its floor. The Mediterranean is thus far more than a body of water. It is a living geological document, a grand testament to planetary change, and a mirror reflecting both the immense, awesome power of natural forces and the profound, and often unintended, consequences of human activity on a system with a long, volatile, and unforgiving memory. The Messinian Salinity Crisis, for all its unique and dramatic specifics, is far more than a regional historical anecdote. It stands as a powerful, globally significant case study, a veritable Rosetta Stone for deciphering the complex behavior of our planet's integrated climate system. It provides a validated, real-world model for understanding the cascading consequences that unfold when a large marine basin is isolated from the global ocean, offering crucial, evidence-based insights for predicting the outcomes of similar, though often smaller-scale, environmental crises happening today. The tragic fate of the Aral Sea in Central Asia serves as a chilling, human-caused analog. Once the world's fourth-largest lake, the Aral Sea has been largely transformed into a dry, salt-encrusted desert over just the past few decades, a direct result of the Soviet-era diversion of the rivers that fed it for cotton irrigation. While the timescale is dramatically compressed, the fundamental physical principles at work are a direct parallel to the Messinian process: a catastrophic shift to a negative water budget, a precipitous drop in water level, a skyrocketing salinity that annihilates the native ecosystem, and the creation of a barren, salt-encrusted landscape that generates toxic dust storms. The Aral Sea is a stark, sobering demonstration that the lessons encoded in the Mediterranean's 5 million-year-old rocks are not academic abstractions. They are urgently relevant, immediate principles for understanding and managing the environmental impacts of human activity in the present day. Furthermore, the sedimentary archive of the Mediterranean serves as a giant, natural laboratory for studying the intricate workings of the global carbon cycle and its profound relationship with climate change. The cyclic deposition of sapropels, those distinct, dark, organic-rich layers interleaved with the Messinian salt and marl, provides a direct, high-resolution record of past biological productivity and carbon burial. These layers tell a story of rhythmic climatic pulses. During precession-driven wet phases, intensified monsoon rains over North Africa would have washed vast quantities of nutrients into the isolated Mediterranean lakes. This nutrient surge would have fueled massive blooms of algae and other plankton at the surface. When these tiny organisms died, their carbon-rich remains sank into the stagnant, anoxic bottom waters where decay was slow, allowing the organic carbon to be preserved in the sediments, effectively drawing down carbon dioxide from the atmosphere and sequestering it in the geological record for millennia. This process is a natural, large-scale analog for some of the proposed geoengineering schemes designed to mitigate modern anthropogenic climate change, such as ocean iron fertilization. By meticulously studying the rates, scales, and ultimate consequences of this natural carbon sequestration in the past, how much carbon was buried, how it affected global climate, and what the ecological side effects were in the basin, scientists can build more robust models to assess the potential efficacy, risks, and unintended consequences of such deliberate interventions in our planet's future. The extreme environments of the dying Mediterranean also hold profound implications for the burgeoning field of astrobiology and the ongoing search for life beyond our own planet. The hypersaline, anoxic, and chemically exotic conditions of the final Messinian lakes are among the best terrestrial analogues we have for the kinds of environments that may have existed on the early Earth, or that may still exist in the subsurface of other worlds. The extremophile microorganisms, the halophiles, methanogens, and sulfate reducers that were the sole biological survivors of the crisis, demonstrate the astonishing tenacity of life and the alternative biological strategies that could potentially support life in the subsurface brines thought to exist on Mars, or in the global, salty ocean believed to lie beneath the icy crust of Jupiter's moon Europa or Saturn's moon Enceladus. By studying the biomarkers and isotopic signatures left by these microbes in the Messinian sediments, scientists are essentially refining their toolkits for detecting evidence of past or present life on other planets. They are learning what to look for and how to interpret the chemical whispers of biology in a harsh, alien-like environment, using the Earth's own dramatic history as the ultimate training ground for the next great age of interplanetary exploration. On a grander, more philosophical scale, the Messinian Crisis is a masterclass in Earth system science, offering a profound illustration of the concept of tipping points, or threshold behavior. For millions of years prior to the event, the Mediterranean existed in a stable state as a normal, open ocean. The tectonic movements that eventually closed the Gibraltar portal were incredibly slow and incremental, perhaps moving at rates of only millimeters per year. The system resisted change, absorbing this slow pressure. But once a critical threshold was crossed, the complete and final isolation of the basin from the global ocean, the system did not respond in a linear, gradual fashion. It flipped catastrophically and irreversibly from one stable state, a full, well-mixed sea, to a completely different, alternative stable state, a dry, hyper-arid desert basin. This nonlinear, abrupt response is a hallmark of complex, interconnected systems, and it is a pattern we see with increasing alarm in components of the Earth's climate system today. The slow, steady increase in atmospheric CO2 from human activities may be pushing the planet towards similar critical tipping points, such as the irreversible collapse of the Greenland ice sheet, the dieback of the Amazon rainforest, or the shutdown of major ocean circulation patterns like the Atlantic meridional overturning circulation. The consequences of crossing such thresholds would be rapid, dramatic, and largely irreversible on human timescales. The Mediterranean's past thus serves as a stark, geological warning of the latent, explosive power contained within seemingly stable and robust planetary systems, reminding us that slow, incremental change can suddenly lead to rapid, catastrophic transformation. Finally, the story of the Mediterranean's death and rebirth is a humbling narrative that forces us to recontextualize the entire human experience within the deep, flowing river of geological time. Our entire recorded history, the breathtaking rise and fall of empires, the dazzling development of art, science, and technology, has all occurred in the brief, unusually stable climatic window of the Holocene epoch, the 11,700 years following the last ice age. The Messinian event and the ice ages that followed remind us with absolute clarity that the Earth is inherently a dynamic, changing planet, capable of changes far more dramatic and profound than anything humanity has ever witnessed. The forces of plate tectonics and orbital cycles operate on timescales that utterly dwarf our own, capable of emptying entire oceans, carving continents, and transforming global climate. This deep time perspective is not meant to trivialize or diminish our current environmental challenges. On the contrary, it underscores the profound and unprecedented responsibility we now hold. For the first time in the 4.5 billion year history of Earth, a single species, Homo sapiens, has become a geological force in its own right, capable of altering the climate, chemistry, and biology of the planet on a scale and at a rate that rivals the great natural forces of the past. The ultimate lesson of the Mediterranean is therefore not one of futility, but one of power, consequence, and wisdom. It teaches us to respect, with the utmost seriousness, the delicate, interconnected balances that sustain the world as we know it, for we now possess the knowledge, drawn from the rocks themselves, that those balances can be broken, and that the path to recovery, should we force the system past its limits, will be long, difficult, and will ultimately be dictated not by our desires, but by the patient, inexorable, and majestic rhythms of the earth itself. As our long and immersive journey into the deep time of the Mediterranean finally draws to its gentle close, let us pause one last time, not to analyze or dissect, but to simply absorb the sheer scale, the grandeur, and the profound quiet of the story we have traced together. It is a narrative that begins not with a bang, but with the slow, inexorable, grinding convergence of continents, a tectonic dance spanning millions of years that gradually, inevitably, sealed the gates of a sea, turning a vibrant ocean into a captive lake. We have stood as silent witnesses to the consequences of that closure, the silent, terrifying, and relentless retreat of the waters, the dramatic emergence of a new, sun-scorched continent 2 miles deep, a surreal world of blinding white salt plains, blood-red brine lakes, and vast, dusty deserts lying under a sky perpetually devoid of clouds and life. We have heard in our mind's ear the theoretical, earth-shaking roar of the Gibraltar waterfall, a sound to define an epic as it poured for a century, a relentless, monumental deluge refilling the empty abyss, drowning the ancient desert under a churning, newborn ocean. And we have seen how the salt, once buried, never truly rested, how it continues to flow and writhe and shape the underworld to this very day, creating the hidden structures that hold our modern energy wealth and the subtle instabilities that pose ever-present threats to our coasts. This entire epic is a powerful, humbling testament to the relentless dynamism of our planet. The ground upon which we walk, the seas we sail, the coastlines we cherish, they are not permanent, fixed features in a static world. They are fleeting moments, temporary arrangements in a continuous, billion-year saga of transformation. The Mediterranean Sea, so central to human history, culture, and identity, is itself a transient entity. It has not always been here in its current form, and it will not always be here in the future. The same tectonic forces that created it, nearly destroyed it, and then resurrected it, continue their slow, patient work. Millions of years from now, the map of this region will be as unrecognizable to us as the map of the Messinian world is today. This deep time perspective, this view from the mountain of geological ages, is a form of liberation from the myopic anxieties of the present moment. It is a reminder that we are but brief participants in a story far larger, more majestic, and more enduring than ourselves, a story of continuous, majestic change where crises are followed by renewals and deserts are transformed into seas. For you, the listener, now settling into a state of deep relaxation, drifting in the quiet space between wakefulness and sleep, let this story be a source of profound and abiding calm. Allow your mind to embrace the immense, slow patience of geological time. Picture the countless grains of salt, crystallizing one by one, accumulating in thick, rhythmic layers over tens of thousands of years. Feel the stately, deliberate, centimeter-per-year pace of the flowing salt domes, shaping the underworld with a force that is both gentle and irresistible. Hear the deep, resonant silence of the empty basin, a silence that lasted for hundreds of thousands of years, broken only by the moan of the wind and the crack of a contracting salt pan. This is the true rhythm of the earth, a rhythm infinitely slower and more stable than the frantic, buzzing pace of modern human life. To contemplate it is to allow your own mind to slow, to find a still point in a turning world, to release your personal cares and worries into the vast, accepting expanse of deep time where they are gently dissolved into perspective. The evidence of this incredible history is not hidden away in remote laboratories. It is all around us, hidden in plain sight, woven into the very fabric of the region. It is in the specific, slightly elevated salinity of the seawater itself. It is in the unique, relative poverty of its deep-sea life, a community still recovering from a near-total wipeout. It is in the oil and gas we extract from the complex traps far beneath the seabed, traps formed by the Restless salt. It is in the deep, buried, and sediment-filled canyons of the Nile and the Rhone, which now guide the flow of fresh water deep underground. And it is in the very shape of the coastline we love and cherish, the dramatic reefs, the sheltered harbors, the scattered islands, all sculpted by the rising waters of the Zanclean flood. The next time you look upon the Mediterranean, or indeed upon any sea, remember that its placid, azure surface is a mask, a tranquil veil. Beneath it lies a hidden history of fire and ice, of salt and flood, of deserts and waterfalls on a continental scale. This knowledge does not diminish the sea's beauty. It enriches it with a profound and awesome depth, layering its tranquil present with the echoes of an unimaginably dramatic past. And so, we quietly take our leave from the whispering depths of the Mediterranean, this sea that was lost to the world and then gloriously found again. Its story is now a permanent part of our planet's memory, a dramatic and indelible chapter in the grand, ongoing biography of Earth. It is a story that reminds us of the awesome power of change, the breathtaking resilience of life, and the beautiful, terrifying, and endlessly dynamic nature of the world we are so fortunate to call home. Let the final echoes of this ancient cataclysm, the profound silence of the salt desert, the distant roar of the great waterfall, the slow, patient flow of the subterranean salt, wash over you now. Let them lull you into a peaceful, restful state, comforted and humbled by the knowledge that you are part of a story more epic, more wondrous, and more enduring than any fiction. Thank you for joining us on this slumber expedition. May the deep, resonant peace of geological time guide you into a tranquil and restorative sleep. Good night.